Good afternoon, everybody. Thank you for coming to this week's DeFord lecture series. We're very happy today to have Jacky Austermann joining us. Charlie Cairns is going to introduce Jacky in just a minute, but first let me thank you for coming. As many of you know, the DeFord lecture series has been a tradition in the Department of Geological Sciences here at UT since the late 1940s, originally called technical sessions. And it has been a tradition in the department where both students and faculty and outside researchers can present their cutting edge research from all the different aspects of the geological sciences. The series is named after Ronald Kinnison DeFord, who was a faculty member here in the department back joining the department in 1948. He worked as a graduate advisor in the department from 49 to 1967, and he also supervised 19 PhD dissertations and 126 master's theses. Among his many contributions to the department, he was instrumental in organizing and running technical sessions for many years, and so it's been named in his honor to recognize those contributions. So we're very happy to have Jacky Austermann joining us today, continuing this tradition of bringing cutting edge research to the Jackson School. And to tell us just a little bit more about Jacky and the work that she's going to present is Charlie Cairns.
Good afternoon. Thanks, John. And it's a pleasure to introduce Jacky Austermann. We've been in contact over the last few years with some of our students working in the Pleistocene, Holocene system of the Bahamas, and her group at Columbia, and then Andrea Dutton's group at Florida and out Wisconsin have been really kind of leading the way in reconstructing past sea levels and trying to understand the interaction between ice sheets and sea level indicators in different parts of the planet, but certainly the Bahamas is one of the key areas. So Jacky actually got her bachelor's degree in physics at the Technical University of Darmstadt, and then a master's in geophysics at Munich. And then she got her PhD at Harvard, working with Jerry Mitrovica, who's kind of seems to be like the developer of the concept of dynamic topography. And that was a big part of Jacky's PhD, was kind of understanding and developing her own approach to reconstructing the changing shape of the physical Earth, and how it responds to loading from ice sheets and unloading through time. Did a postdoc at Cambridge University, and then in 2018 she became an assistant professor at Lamont, Doherty, and this is a spectacular trajectory. I noticed on their website that she was also just named one of these. What is it, Jacky? One of these. Got a very nice award fellowship for next year, from the research she's been doing. So that's, just a further indication that she's one of the leaders in this area of research. And that's what we're trying to do, is bring in young people with new ideas that are really leading the field. And this one is of great interest to me. I'm pretty simple when it comes to things like physics. So I go out and I find corals at a certain elevation above sea level, and I assume very naively that is the fossil sea level indication. And of course, that turns out not to be the case. It's a little bit trickier than that. And so we need to have people like Jacky who can come in and unravel this kind of complex history of sea level and glacial isostatic adjustments and dynamic topography to really put the story together fully. So I'm certainly taking notes and trying to learn as much as I can. I know my students are as well. So we've been trying to get her here for the last 2 years in person, but still hasn't quite worked out yet. So that's on the list of things to do once we sort things out. So I don't want to take up any more of your time, but we sure are happy that you're here and giving a presentation, Jacky, and we're looking forward to it very much.
Thank you so much, Charlie. Thanks for the kind introduction and the invitation to come and talk to you about some of the work that I've been doing with a lot of collaborators over the last few years. And Charlie, I see your background now matches the color palette of my title slide, which is a picture from Long Island in the Bahamas, which is part of what I will be talking about today. So I want to talk about how high last interglacial sea level was, and I'm going to talk about it starting from the rock record to all of the geophysical corrections and solid earth deformation processes that we think about, and hopefully arrive at an estimate of global mean sea level during the last interglacial, as well as come up with an estimate of both the Antarctic contribution and the Greenland contribution to sea level during this time period. So before I dive in, I want to acknowledge that a lot of people have contributed to this work over the years. Most importantly, Blake Dyer, who was a postdoc at Lamont for a long time and now is a assistant professor at the University of Victoria, and Mo Ramo as well. And then I'll talk those, they have been contributing particularly to the Bahamian work. And then Rob Burnett and Tasha Barlow and others have contributed to work on last interglacial sea level in Northwest Europe, which I also will be talking about, in addition to all of these other great people down here. Okay, so before I dive into last interglacial sea level and how we reconstructed, et cetera, I want to kind of set the stage a little bit more broadly and think about why we worry about and why we even try to reconstruct sea level during this time period. And luckily for us, the sixth assessment report from IPCC came out just this year and really motivates this question, I think, really nicely. So what I'm showing you here is a time series from this report of sea level change from the 1950s to 2100. Global mean sea level is on the y-axis here. And what they're showing is that there's an observational record down here, and then different projections based on different emission scenarios, with obviously kind of the blue records are low emission scenarios and the red records are high emission scenarios. And what you see here as well is this dashed red curve, which is, and I should say, right, so these end up with 0.5 meter to 1 meter of sea level rise relative by the end of the century relative to 1900. And then this dashed line here is what they call a low likelihood, high impact storyline, which includes ice sheet instability processes. And so this is essentially to say here, if in this high emission scenario, we think sea level is going to be about 1 meter by the end of the century relative to the 1900s. But it could also be 1.7 meters, right? Almost double if we're rounding up here, but significantly higher if the ice sheets are just more unstable. And it seems not super likely, but we can't rule it out and would have a really high impact. So this scenario is really the scenario we want to understand better. And if we look at the projection out to 2300, the projections show us that for low emission scenarios here in blue, again, sea level is probably going to rise by about 0.5 meter to about 3 meters, which tells us that even in low emission scenarios, we're locked in to a certain degree of sea level rise, which I think is also in agreement with a lot of the stuff that I will be showing you later today. But if we look at the high emission scenario, it starts at about 2 meters to 7. But then, as they state in the report, sea level rise greater than 15 meters can also not be ruled out within this high emission scenario. So this goes in line with this extrapolating this low likelihood, high impact storyline. So where does that come from? So it comes from processes in the ice sheet, such as, for example, the marine ice cliff instability that can lead to a rapid collapse of the ice sheet. And a lot of these processes have been kind of developed and thought about within the glaciological community, but then really been pushed by folks who've been studying the paleo ice sheet modelers who've been also studying the paleo record. And I'm going to demonstrate this here with this figure. So this is from a paper from Rob DeConto from just this year. And what he's doing is he's running an ice sheet model for the Antarctic ice sheet, and he's forcing it with the conditions associated with the last interglacial, which are about on average, on average 1 to 2 degrees warmer than pre-industrial times. And then he predicts a global mean sea level associated just with the Antarctic melt contribution in response to this warming. And if he doesn't include any of these instability mechanisms, that sea level only rises pretty slowly. So this is in thousands of years here. However, if we include a lot of these instabilities, sea level can rise very quickly and up to about 4 meters here before it plateaus. So all of these lines are different. It's like a big model ensemble. And what he's using to distinguish between which models to then use in projections for future sea level change is he uses the Last Interglacial sea level estimate to calibrate this model. And they're using 3.5, they're assuming that 3.5 to 6 meters of melt came from the Antarctic ice sheet, which rules out any of these sort of more stable ice sheets and leads to these ice sheets models that have parameters in them and processes in them that make them relatively unstable relatively quickly. So whether the Last Interglacial target now is 3.5 meters to 6 meters, or whether it is 1 to 2 meters, has a huge impact on these projections that then are used to make predictions of future sea level change. And so this has been really influential in driving a lot of these high sea level storylines. So what we're going to be talking about is, where does this number come from? How do we know how much higher sea level was during the Last Interglacial, and how much higher would how high the Antarctic contribution was to Last Interglacial sea level? And we're going to revise this estimate at the end of the talk. Before diving into this, I want to just, after this kind of very quick motivation why we're interested in Last Interglacial sea level, I want to take one step further back and just give a little super brief overview of when the Last Interglacial was and what the climate system has been doing since. So I'm going to do this by showing you the oxygen isotope stack here. So this is the last 5 million years. 5 million years ago is here, all the way to the present. And we have the oxygen isotope record, everything that plots sort of at the top of this curve are times when it was warmer and there was less ice around, and everything that plots at the bottom were times when it was colder and there was more ice around. And as you all know, we've been, especially in the Pleistocene, we've been going through these ice age cycles that have become larger in magnitude and have become longer in time span. So if we look at what these cycles look like in terms of ice distribution and change over time, this is just one simulation here that shows you the growth and decay of these late Pleistocene ice sheets that held about 120, 130 meters of water in them and oscillated between glacial maxima and glacial minima. And you see the ice sheets, most of the ice sheet variation happens in the Northern Hemisphere here in the Laurentide, and the Eurasian ice sheet and the Antarctic ice sheet and the Greenland ice sheet varied as well, to a much smaller amount though. And you also see the kind of sea level change that goes along with that ice growth and ice decay. So the time period today, we are in the Holocene, or in the end of the Holocene, right? And we are in an interglacial during a warm period. This is the glacial maximum down here. And the time period I'm talking about is the Last Interglacial. So this is 130,000 years ago. And global average temperatures were around half a degree to 1.5 degrees higher than pre-industrial values. And as such, this serves as a time when temperatures were warmer. Therefore, we can look at how much smaller ice sheets were, and we can learn about how ice sheets respond to warming. There are other time periods that I marked that you might have heard about or seen in terms of this in that kind of context, like the mid-Pliocene warm period that I've looked at as well and thought about in terms of the temperatures were about 2 to 3 degrees warmer. Early Pliocene temperatures were maybe up to 4 degrees warmer. So we can use these past time periods to really understand ice sheet stability and response to continued warming. And in this talk, I'm just going to focus on the Last Interglacial here. So what are the values that the IPCC report, and really I would say most up-to-date literature tells us about global mean sea level, as well as the contributions of different ice sheets? Well, in the last interglacial, in the IPCC report, the range that is cited is that sea level was 5 to 10 meters higher than today. That the Antarctic contribution was maybe on the order of 4, but between -2 and 8 meters. So this is obviously a pretty large range here. And the Greenland contribution was 2 meters with a range of 0 to 7 meters. And just to give you context of what these numbers represent or mean in terms of ice volume, I'm showing you here the amount of sea level rise that would be caused if you were to melt that entire ice sheet. So if the Greenland ice sheet was to melt, you would get up to around 7 meters of, on average, global mean sea level rise. So, which also means that a Greenland contribution of 0 to 7 meters means none of it melted during the last interglacial compared to today, or all of it melted during the last interglacial compared to today. The Western Arctic ice sheet, if you have all of it, is about 5 meters, 4 or 5, depending on where exactly you choose kind of the cutoff. And then the largest amount of ice is stored in the Eastern Arctic ice sheet here. And again, 4 meters, we believe that the Western Arctic ice sheet, due to its major marine-based sectors, is probably most susceptible to retreat and melt. So that would probably be the first one to contribute to melting. But then there are also marine-based sectors in the Eastern Arctic ice sheet that might contribute a smaller amount. And again, the range remains quite large. So how are these sea level, how do people end up with an estimate of 5 to 10 meters of sea level, of global mean sea level during the last interglacial? I'm gonna kind of walk you through the steps quickly now, and then I'm gonna walk you through those steps again very slowly for the rest of the talk. So essentially what we start with is an estimate of local sea level. This can be a coral or a sedimentary feature at one given location that we can date and put our finger to it and say, this is how high last interglacial sea level was at this location. Next, we need to correct this elevation for any of the geophysical processes that Charlie already mentioned. We need to correct for glacial isostatic adjustment, dynamic topography, tectonics, sediment loading, anything that makes a local, an island like the Bahamas go up or down over since the last interglacial. Because if I'm standing on the island and I'm measuring sea level, I'm looking at sea level, I don't actually see, I don't know whether global mean sea level is going up or down, or whether it's the islands going up or down. I see kind of the combined effect of all of it, right? So when if I want to extract back out how much of it really comes from the ice sheet, I want to correct out any uplift or subsidence associated with the solid Earth. That leads us to what I'm going to call a corrected local sea level. And then there's one more step that we need to account for, which is that as ice sheets melt, and now I'm particularly talking about during the interglacial. So during the last interglacial, as the Greenland ice sheet contributes to melt, as the Western Arctic ice sheet contributes to melt, it doesn't cause a sea level signal that is uniform across the globe, but it has a very distinct geographic pattern. And that's just the sort of mechanism is sort of portrayed here. And we're going from sort of the solid line to the dashed. So as the ice sheet melts, it gets smaller. That means there's less load on the solid Earth. We get rebound in this area. And not only that, but it also affects the gravity field, because before the ice sheet melted, it attracts a lot of the water towards it. And then after the ice sheet melted, that kind of attraction, gravitational attraction, starts to fade away, and the surface of the Earth, the surface of the water kind of moves from what's colored in here to that dashed line. So if you're standing close to the ice sheet, the sea level signal that's actually observed is one of sea level fall, even though the ice sheet is melting. And it's sea level falling because the solid Earth is uplifting and because that loss of gravitational attraction. So there's a very distinct geographic pattern. It's referred to as a fingerprint of ice melt. So here's a fingerprint of ice melt associated with the Western Arctic ice sheet. So as 1 meter of Western Arctic ice melts, so 1 meter meaning 1 meter that the amount of ice that if you melted, it would lead to a global mean sea level rise of 1 meter, you would get this specific distinct pattern of local sea level change. So you would get sea level falling close to the ice sheet, and you'd get sea level rising away from it, but rising less than the mean in its proximity and more than the mean kind of far away from it here. So if we reconstruct sea level at one given location, we also need to take that into account. And while it's sort of, this part is a bit of a blessing and a curse, it's a curse because we have one additional process that we need to correct for. But it's a blessing because if we have two locations where we have sea level data or more, we can potentially identify how much melt comes from different ice sheets, right? If we have a sea level record here in the Bahamas, and if we have a sea level record in Patagonia, and they show us a different magnitude of sea level rise, it probably tells us that, or exactly this sort of amount of difference in sea level rise, we probably know that that melt came from Antarctica, versus we can also look at the fingerprint associated with melting from the Greenland ice sheet, which looks sort of flipped here. And that would, and then also the sea level signal would be flipped, and we could actually fingerprint and identify that the melt came from the Greenland ice sheet. So this second part where we correct for that distinct signal of sea level change associated with ice melting during the interglacial is the step where we can also start to associate how much melt comes from the Greenland ice sheet and how much melt comes from the Antarctic ice sheet if we use more than one record. So before I go through this again, but slowly with a lot of examples, I just want to highlight why this work is difficult to do and why uncertainties in these estimates and ice sheet reconstructions remain so large. And I want to point to two aspects in this kind of chain of corrections that we're doing here. One is that reconstructing local sea level is hard. And it's hard because it's hard to tie, if you have a sea level indicator that tells you how high sea level was, it's not trivial to know, you know, if you have a fossilized coral, for example, did this live a meter below sea level or half a meter or 4 meters or 5 meters? So actually understanding the relationship to past sea level of an indicator can be difficult. And then also getting a good chronology, so actually getting an age on that indicator can be very difficult. So this is a very tricky part. And then the other part that's very tricky is quantifying all of these corrections in a meaningful way, because they all have a lot of uncertainties. And I will talk about those at length. Okay, so here's sort of this walking through these steps now again, but taking a little bit more time for each. So I'm going to give you an example of a local sea level record from the Bahamas. Then I'm going to talk about the glacial isostatic adjustment correction that we have to do for this record. Then I'm going to present our corrected local sea level from the Bahamas. Alongside, I'm going to present another record that I'm going to bring in at this point, which is from Northern Europe. And then we're going to use those two records to actually attribute how much melt comes from the Antarctic ice sheet and how much melt comes from the Greenland ice sheet during the last interglacial. Okay, so looking at the Bahamas, this is a very familiar place to many of you in the department, which is very exciting. So we're looking at this carbonate platform here, and I'm gonna specifically show most of the pictures that I'm gonna be showing you are from Crooked Island here. This carbonate platform has a ton of sediment, which makes for great, nice beaches and a lot of kind of flat bathymetry and the beautiful islands that you probably associate first sight with the Bahamas. It's a really great place to study paleo sea level because of many reasons. One of them is that there's such a high sedimentation rate and such a high rate of a fast rate of cementation that essentially the geology is frozen in space. and time very quickly. So I'm showing you here a picture of a fossilized dune system where you see kind of these steeply dipping dunes. And this, I don't even remember whether this is I think a Last Interglacial one here, but it's just this dune that formed and then cemented and recorded the geology in place. And if we find an Aeolian dune, we know that this formed above sea level. In addition, it's a great place to study sea level because there are a lot of indicators that trace. So not only is it recorded, there's a lot of material to record it. It actually records it very well, but there are also a lot of indicators that record specifically sea level. So one of them are fossil corals. On the left here is a living coral. On the right is the fossil analog. And you see there's some kind of beach sand that formed, prograded over it afterwards. But you see underneath here is this really nice coral head that's hasn't been altered much. Here's another indicator. So on the left, again, the modern analog, just kind of these beach ripples. On the right is the last interglacial analog. These ripples here in this last interglacial unit that are really a place where you can, put your finger on knowing exactly this is where last interglacial sea level was. You don't necessarily, getting an age on these features is a lot more difficult than on corals. A lot of the ages that we're going to be using are from corals, but these features are better at constraining the elevation of sea level. Here's one last example. This is sort of looking at the unit from the top. You see these kind of holes. If we look at it from the side, and we're actually going to zoom in, you see these kind of chutes here. And these fenestrae form essentially at the swash zone. If you go to the modern beach today and you stand in the area where the waves come in and out, as the waves go out, you see the air bubbles popping up on the beach. And that's what's, again, here frozen in time and fossilized. And we know exactly this place at one point was for sure at sea level to form these features. So the work that I've started contributing, but really Blake Dyer and Moremo have done over a long time, over a few years already, is to go around the islands and look for the highest marine to Aeolian change on as many islands as we could visit. And these elevations are shown here. So the highest in the north on New Providence and Eleuthera, about 6 to 7 meters. The highest elevations are a little lower, further in towards the south, and then even lower to even further down. So what is interesting about this, obviously, is that there is some spatial variability in that highest marine to Aeolian, so the highest sea level. And this is just kind of shown again here. Those are different cross sections from these specific locations, where you see really the upward shallowing. So, I mean, this is very small, but in each of them, we're looking for the upward shallowing sequence and for the highest sea level on the island that we can identify. The reason, and I'll get into this a little bit later when I talk about GIA, the reason why we're looking for the highest sea level is that because of the process of glacial isostatic adjustment, we would expect sea level to rise over the course of the interglacial, and therefore the highest sea level would probably form late in the interglacial. So it gives us some way of associating an age with those elevations, and I'll talk more about that later. In addition, and I'm not going to go into any detail here, but all of this Bahamas work was published earlier this year, and you can find more details on that. But in addition, Blake Dyer also trained a neural net on the islands where we had the highest elevations to then map the highest elevations at additional islands and use those just as marine limiting data points. So those are shown in yellow. In addition, we have coral ages on some of these islands. The light green ones are ones where we have coral ages that also pass specific kind of open closed system and diagenesis screening criteria. And in darker green are new ages that weren't actually included in a lot of the work that I'm going to show you here. Those have just come out this year out of the work, and the paper is just being in prep at the moment, but I'll show some of those in comparison to our predictions later on. So this is the data set of last interglacial local sea level reconstructions that we are going to work with. The next thing that we're going to do is we're going to correct it for any geophysical process that makes the islands go up or down since the last interglacial. And the main one that I'm going to talk about is glacial isostatic adjustment, or GIA for short. And glacial isostatic adjustment, what is that? It's the viscoelastic response of Earth's solid surface, the gravity field, and the rotation axis to changes in ice and ocean load. So as ice sheets grow, they press down on the lithosphere and on the mantle underneath, causing flow towards the periphery of the former ice sheets or of the ice sheet. And this causes, because of mass conservation, uplift of these areas around the ice sheets, which are generally referred to as the peripheral bulge or the forebulge. During the interglacial, ice sheets melt, and the area underneath the ice sheet experiences uplift or postglacial rebound. And the areas that were formerly high, that were formerly the peripheral bulges, are starting to subside. We generally understand this process pretty well, and we can make predictions of this deformation. And the two things that we need to make those predictions are we need to know what the viscosity is of this medium underneath. The viscosity tells us something about the time scale of how quickly the flow occurs. And then we need to know the past ice sheet history. We need to know how big the ice sheets actually were and how much they extended in order to understand, for example, the extent and the shape of the peripheral bulge. So to give you a sense of what this pattern looks like, I'm showing you here a map of a numerical prediction of present day sea level change that's driven just by the last deglaciation. So this is how much sea level changes today around the globe, not because of ice melting, but just because the Earth is still adjusting to what has happened over the last 30,000 years. And what you see is that, clearly you see outlines of former ice sheets, the Laurentide ice sheet here, the Fennoscandian ice sheet here, or the Eurasian ice sheet here. And we're looking at sea level falling, which is equivalent to the land uplifting. So this is postglacial rebound here. And around those areas that are rebounding, we have sea level rise, which is the peripheral bulge subsiding. And we see this around most of the major former ice sheets. And there's more structure in the far field associated with hydroisostasy, so loading of water loading and unloading. And I won't go into the detail of too much of that today. But the main aspect here is, as I said, the sort of near field effects of rebound and peripheral bulge subsidence. And we actually can measure this really well in the present day sea level change along the US East Coast, where we see that sea level rises more than the global mean because the US East Coast is on the peripheral bulge and is actively subsiding. And in places like the Carolinas, that actually contributes half of the signal of present day sea level rise is due to GIA. The other half is ice sheets melting, thermal expansion, mountain glaciers, etc. So it's an ongoing process that we understand somewhat well over the deglaciation, and we definitely observe that very much today. So how much did GIA deform the solid Earth over the last interglacial? Well, we can make a prediction, and we need to make assumptions about these two parts here. For the Earth structure, we're going to assume an elastic lithosphere, a viscosity in the upper mantle, and a certain viscosity in the lower mantle. in the real Earth is not just layered into a lithosphere, an upper mantle, and a fixed lower mantle, but actually has some heterogeneity. And we know this, of course, from seismic tomography. I'm not really the way we're gonna deal with this here today is by just varying. We're gonna look at a suite of model runs that vary upper mantle viscosity, that vary lower mantle viscosity. I do have a paper that came out earlier this year as well that looked at how much this 3D variability affects last interglacial sea level, but I'm not really going to talk about that more today. So that's input number one. We're just going to vary viscosity structures within a reasonable limit. The next thing that we need to prescribe is how big the ice sheet was specifically at the glacial maximum that preceded MIS 5E. And I should have probably said at the beginning, I'm talking about the last interglacial as just MIS 5E, which is just this high stand here, not rather than the entire MIS 5 time period. So we need to know how big the ice sheet was and how quickly it melted from stage MIS 6 to 5E. And it turns out that we actually don't have a great grasp on how big the Laurentide ice sheet was during this time period and how big the Fennoscandian ice sheet was during this time period. If we look at the last glacial maximum, most of the excess ice was stored in the Laurentide compared to the Fennoscandian ice sheet. So these numbers here are again the sea level equivalent. If you were to melt all of that ice, how much would sea level rise on average? So we have about 88 meters in the Laurentide, 20.5 meters, 23.5 meters in the Fennoscandian ice sheet. For stage 6, this might have looked quite different. The Fennoscandian ice sheet was probably a lot larger. So this is about twice as large here in one reconstruction, and the Laurentide possibly smaller. Or the Fennoscandian ice sheet might have been even larger, 70 meters. And again, the Laurentide smaller as a result. So we don't exactly know how big the Laurentide ice sheet was, which is of course very important if we want to reconstruct the forebulge, which is and GIA, which affects the Bahamas and places around the world. And this actually gets me to one point that is always hard to motivate in the beginning, but now is a good time to motivate it, which is why we go to the Bahamas in the first place, in addition to all of the reasons why it's good for recording sea level. But it is also a really good place to look at this GIA, constrain all of these uncertainties in our GIA models. So here are 3 different figures that show sea level at the end of the last interglacial. If you have in kind of a reference GIA simulation, you see the rebounding area, the peripheral bulge area. If this is a prediction, if the lower mantle is a lot stiffer than in the reference scenario, or if the Laurentide ice sheet is a lot larger. So the main takeaway here is that the predicted change in the sea level in the Bahamas from the north to the south, this gradient across the archipelago, is very sensitive to these choices in our GIA model. It's very sensitive to the viscosity structure. It's very sensitive to the size of the Laurentide ice sheet, which is not surprising, right? It's close enough to the Laurentide ice sheet that it's sometimes on the peripheral bulge. And therefore, if the viscosity structure changes, or if the Laurentide ice sheet changes, it moves on to or off the peripheral bulge, or the peripheral bulge gets steeper or flatter. And so we can leverage that spatial information that we get from our data to actually limit which GIA models are most likely, which parameters in our GIA models are most likely. And so that's exactly what we're going to do. We're going to use all of the data that I described before. We're going to compare them to a suite of almost 600 GIA models that vary viscosity and ice structure, and look which models do well in explaining not the absolute magnitude, because we don't know yet how much ice actually melted during the last interglacial, but which models do well in explaining the geographic variability in the data here. And for that, we are going to assume that there is and I'm going to show time series a little bit later, but that these blue, the maximum elevations form towards the end, was prescribes some uncertainty, but towards the end of the last interglacial. And the coral ages, of course, corals have elevations with specific ages associated already. And so here's the result of that exercise, and it's kind of a messy figure, but we have each tile here is a comparison between a GIA model prediction and an observation. And we're varying, you don't have to worry about the exact which square is where. We're varying all of the viscosity structures, and we're varying the size of the ice sheet. Most notable, this is the big Laurentide ice sheet, smaller, 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 smallest Laurentide ice sheet. So top to bottom is kind of size of Laurentide ice sheet. Blue means the data and the models don't agree. Yellow means the data and the model agree well. And again, we're just using kind of the spatial information in our data. And we're seeing that there is a subset here that is more yellow than a lot of the rest around it, which means that probably the Laurentide ice sheet was much smaller during the stage 6 than the last glacial maximum. Probably on and towards here, this was 56 meters of ice sea level equivalent. And now we're going to use all of these GIA models to correct our data, but we're going to weight them by the one using mostly the ones that do really well in fitting the spatial variability. We're going to, before I show you that, go to step 3, GIA corrected sea level. We're gonna add one more aspect here, which is that we're also gonna correct for long-term subsidence based on some cores from the Great Bahama Bank. We're gonna assume a constant subsidence based on those of 2.5 meters plus minus 0.5 meter since the last interglacial. There might be some spatial variability. There might be some larger uncertainties. This is quite uncertain. But, and I can talk about the process of what might drive that or not later on, but we're going to include that as our contribution of long-term deformation. So rather than using a model-based prediction, we're using observation-based prediction of how much long-term subsidence occurred in addition to GIA. And that leads us to our result number 1. Here, which is our corrected sea level. So this is taking the data, correcting them for the GIA models that do best in fitting the spatial gradient, and including a correction for long-term subsidence. And what we get out is a sea level, or a corrected sea level that peaks at, the peak is up to 5 meters, but the most likely values hover more around 3. Early in the interglacial, so this is early into the interglacial towards late, and then decrease with a little bit of a dip and a little bit of a tiny late rise to about 1 to 2 meters late in the interglacial. So this is already a lot lower than 5 to 10 meters that I cited early on, right? But there's also one more step we need to correct. We need to attribute where this melt comes from, whether it comes from the Laurentide or whether it comes from the Antarctic ice sheet or the Greenland ice sheet. We can look at the local records, and I'm going to just go through this quickly here, but these are now having the global mean sea level prediction and putting the GIA, the local sea level prediction, back in to look at how well our prediction fits the data, and it should fit it really well because the data have been used to construct that global mean sea level curve. Those are all the data from the different sites, the coral data in blue, and the black are the highest marine to Aeolian, and the orange are the highest marine to Aeolian trained with the neural net. There's a lot more to think about here, and I won't go into details, but I just also want to show these are the new ages that we have just gotten this year that still kind of fit quite nicely with the predictions on Eleuthera, Long Island, and Crooked. Okay, so I mentioned there's this last step that we need to do, which is account for the fingerprint. And what we're going to do here now is we're going to bring in that second record, and we're going to bring in a record from Northern Europe here. And the reason this is a great place to add is it's sort of at this edge between white and blue, which is, it's at the edge where sea level change that's driven by Greenland ice melt does actually, what sea level does actually not change at all if the Greenland ice sheet melts. And this is again, this because of this, the gravitational effect and the rebound effect. So if we're detecting any sea level change in this region, it's mostly driven by the Antarctic ice sheet. So we're gonna take these, we have data of sea level. They are based on OSL dating. They have much larger uncertainties than data in the Bahamas. And we're gonna go through that exact same process of using all of these GIA models, correcting for them, correcting for long-term uplift, and coming up with a GIA corrected or corrected sea level curve, which I just showed you the one for the Bahamas. This is the one for Northwestern Europe. It's somewhat higher. It's up, starts at 5 meters, but then also sort of decreases and has less of that sort of second hump. And uncertainties, as I said, are quite a bit larger in here. These are the local records. I won't go into those just for comparison. So now we're gonna end on by putting it all together. So first, what we wanna do is we wanna get an estimate, a better estimate of how much the Antarctic ice sheet contributed. And we're gonna base that on this Northern Europe record, because this record is mostly sensitive to Antarctic melt. And this is sort of shown here. We ran 8 different simulations of Greenland ice collapse. In black shows you that the ice collapse in global mean sea level for that specific Greenland ice sheet scenario. So some models predict, these are ice sheet based models. Some models predict 5 meters from Greenland. Some models predict 1 meter. Some models predict half a meter. But what we actually see, what Northwest Europe actually observes, is shown in green, and is always sort of a very much muted version of the global mean sea level because of that fingerprint. So what we're going to do is we're going to take the GIA corrected sea level in Northwestern Europe. We're going to come up with how much Greenland contributed here, which is very little because of that fingerprint, the location that it has close to Greenland. And we're going to subtract that out. And that gives us our Antarctic contribution. There are also components associated with thermal expansion, mountain glaciers that are extracted here in order to really eliminate and just zero in on Antarctica. So our Antarctic contribution starts at around 5 meters and then lowers to about 2 meters with quite big uncertainties. And what we want to do now is we want to see that this is, this is a prediction just based on the European data, but what Antarctic contribution plus Greenland contribution fits both Europe and the Bahamas, fits both of these 2 locations. And we're gonna, so what amount of Antarctic and Greenland melt is consistent, not just with the European data and not just with the Bahamian data, but with both at the same time. And we're gonna start with just saying, with just using this Antarctic contribution that we have from Europe as sort of our prior knowledge of how much the Antarctic contribution could have contributed. Then we're gonna use the whole range of those different Greenland ice sheet models, scenarios for that range from no melt to 5 meters of melt. And we're just gonna go through and say how much, if I take this contribution from Antarctica with this fingerprint, this contribution from Greenland with this fingerprint, and I add them up, and I get a prediction for the Bahamas, which combination does well in fitting both the Bahamas and the European data. And if we do that, we end up with a much smaller range of predictions of our global mean sea level that is on the top end of the Bahamas and the lower end of Europe, which is not surprising. The European record was a lot higher, right? And we can go back and look at, okay, how much did we in the end take from the Antarctic and how much did we end up taking from Greenland that led to a signal that's locally consistent with both of these sites. And these are the records that we end up with. We end up with a posterior Antarctic melt signal of 2 to 4 meters that likely happened early and decreased over the course of the interglacial. And a Greenland signal that peaked between 2 and 4.5 meters. But that melt can only come sort of late, and really a very late signal is not that consistent with the climatology Greenland, so could happen sort of during the mid-last interglacial. And we can add both of those together again to get our estimate of global mean sea level, which peaks 3 to 5 meters. So here, let me just kind of wrap this up and summarize what I've just kind of walked you through. And I know I'm kind of sped up a little bit towards the end just to give a little bit more time for questions. But the IPCC report gives us an estimate of 5 to 10 meters with quite large uncertainties for Greenland and Antarctica. These estimates are based on very similar approaches that I've been describing to you today, but generally using fewer GIA models, fewer constraints on long-term deformation, data with generally less certain age constraints, but using more sites. I've only used 2 sites, and this is something that's certainly still the part that's work in progress. But from using those 2 sites, what we find is that sea level was not 5 to 10 meters higher, but in fact, only 3 to 5. That the Antarctic contribution, and both the Antarctic and the Greenland contributions, peaked around 2 to 4 meters. Again, the exact numbers, I think this part is still work in progress and will probably be slightly revised, but within this ballpark of numbers. So we are able to limit the uncertainty ranges significantly and end up with at the lower end with an early Antarctic and slightly later Greenland contribution. And if we compare it back to the De Conto et al. Paper that uses the last interglacial as a target for their calibration of ice sheet processes, and we look at our estimate for the Antarctic contribution, we're actually at 2 to 4 meters rather than the 3 to 6, which allows for a much larger suite, many more models that he ran, right, pass through this green window than through the dashed window, which possibly allows for a lower sea level, still higher probably than this kind of high emission scenario here, but lower than this kind of worst case scenario that's shown in the dashed here. So I'm gonna leave the conclusions up that just summarize some of the things again that I mentioned today. And I'm really happy to answer any questions and wanna thank you for attending the talk today. Thanks so much.
The opportunity to thank Jacky. Thank you once again for coming and giving a very interesting presentation. And thank you everybody for joining us this week. And please join us again next Thursday. With that, I believe we can pause the recording, and thank you everybody once again.